Question 16a. All right, let's start this just writing down this equation with these plugged in. So we got that, and then we want to look at the real and imaginary parts. So this is real, that's real. So we get 1 plus cos theta plus cos alpha equals 0, and then the imaginary parts, sine theta plus sine alpha equals 0. Now, since this second equation is a lot simpler than the first one, it's probably a good idea to focus on this one first and see what information we can get out of that. So that will tell us sine theta is negative sine alpha. Now, in the solutions in the marking guide, they've said because of that, theta equals negative alpha. Now, that is not necessarily true just from that information, because you can imagine if we had, like, if theta equals 20 degrees, for instance, then you could have alpha being negative theta, but you could also have this one over here, where alpha is theta minus pi. And that would also satisfy that equation. So we can't actually conclude at this point that theta equals minus alpha. So I'm disagreeing with the marking guide here. What we would like to show, though, as you can kind of see in the diagram, you would expect to get something like cos alpha is plus or minus cos theta, because you can see this one has the same cosine and this one's the negative cosine. So my sort of problem-solving process for this one was that I worked out geometrically what I was expecting to get, and then I sort of looked at this and thought, okay, how can I manipulate that algebraically so that I get that answer? So it was sort of a roundabout way of doing it, but sort of looking at visually what answer we expect to get is usually a good idea in this kind of question. So let's see how we could get this conclusion from that. Well, my idea was to square both sides of this. And then we could do like 1 minus each side. And then that's cos squared theta. And then that would give you this. The cos alpha is plus or minus cos theta. Okay. So now we've got these two possibilities. It's either cos alpha equals cos theta, or it's cos alpha equals negative cos theta. So let's try each one. We could do if cos alpha equals negative cos theta. And then we can plug that into this equation here. And then those cancel when you get 1 equals 0. So obviously that doesn't work. So you could say no solution. And therefore it has to be the other possibility, that cos alpha equals cos theta. And then you would get 1 plus 2 cos theta equals 0. Cos theta equals negative a half. And that tells you theta equals 2 pi on 3, or it could be negative 2 pi on 3. So we'll put a plus or minus. And then what is alpha going to equal? Well, if cos alpha equals cos theta and sine theta is negative sine alpha, then we're going to have alpha is going to have to be the negative of whatever this is. So if theta is positive 2 pi on 3, alpha needs to be negative 2 pi on 3, and if this is negative, this one needs to be positive. So there's a symbol for that, actually. If this is plus or minus 2 pi on 3, we can say that alpha is minus or plus 2 pi on 3. I don't know if they teach that in the schools here, but that just basically means the opposite of whichever one is picked for that. Okay, so there's two possibilities here. We've got z out at 2 pi on 3 and w down here, and then 1 is over here. So you can kind of see how that's going to make an equilateral triangle. Or it could be with the w up here at 2 pi on 3 and z at the negative 2 pi on 3. Okay, now in the solutions, all they said was that this equals pi on 3, therefore it's equilateral, and they didn't really say why they concluded or how they concluded that that was pi on 3. There's a few ways you could do it. I mean, you could say, you know, we've got this isosceles triangle because we know that both of those are 1, and then you could work out what this one is, these little angles here, and then it's the same for the other ones, therefore that angle is pi on 3. Or you could say something like, we know that all these sides are 1, and then we've got this angle of 2 pi on 3 in each part, so you could say that that triangle is congruent with that one, and therefore those 3 sides are equal. I don't think that they're looking for a very detailed proof that they're equilateral triangles. So, you know, however you want to conclude it, we can just say, yeah, they're equilateral. Part 2. Okay, so we have to find the connection between this one and part 1, which was saying that if 1 plus z plus w equals 0, then these will form the corners of an equilateral triangle. So what's the connection between this and this? Well, what we could do is take this equation and divide everything by 2i. So you get 1 plus z1 on 2i plus z2 on 2i equals 0. And because we know that z1 has the same modulus as 2i, this is going to have a modulus of 1, just like z did in part 1. So we know from part 1 that these 3 will form the corners of an equilateral triangle. So they're going to be like this, where there's 1, and then there's z1 on 2i, and z2 on 2i. And z1 is just 2i times this. Now multiplying by 2i is just going to rotate these things by 90 degrees and scale them up. So the 2i is going to be like up here, so the same as that one except scaled up by 2 and rotated around, and then z1 is going to be sort of around here-ish, so that same vector except rotated and scaled up, and then this one's going to end up over here. So you would just need to say something about multiplying by 2i will just create another similar triangle because it's just rotating and scaling. So the way that they wrote that out in the marking guide was this. So you just have to write it out in 4 sentences, basically. Part B. Alright, what I would do first with this one is just draw a picture of what's going on. That's always handy to have. So we don't really know where U and V are, but let's just pick something. So U could be up there, and then V could be over here. So that's an equilateral triangle, or it could also actually be like over there, we don't know. But what can we do with that information? We know that all the angles here are 60 degrees, or pi on 3, if you're working in radians. So we can see that V is just U rotated by pi on 3 in either direction. But we don't know which direction, so I might say let Z equal... No, I would say cis pi on 3, or plus or minus pi on 3, because we don't know which way it is. Now, I haven't seen the cis notation used in the marking guide, so I guess they don't teach that anymore. So that's just the same thing as this. So we can say that V equals ZU, so that just means U rotated by either positive or negative pi on 3. All right, and then what occurred to me to do was to say that V minus U, so that's that vector, that's just the V vector rotated by that same angle. So ZV. So if Z is going anti-clockwise, then it'll be like that. If Z is going clockwise, then V minus U will be that one, and it's still V rotated by Z. So it works either way. And then what I did was I said Z equals, so from that equation, Z equals V on U. And from that equation, it's V minus U on V. So, okay, now we have this. And if I multiply both sides by V and by U, I'll get V squared equals UV minus U squared. And then you can shift that across. Now, this isn't the way that it was done in the marking guide. What they did was they took this equation and they cubed both sides. So V cubed equals Z cubed U cubed. And then Z cubed is actually -1. And then we could rearrange this equation and then factorize that. So you'd get V plus U times V squared minus UV plus U squared equals 0. So either that equals 0, which we know isn't true because, you know, they're not 0, these vectors, and they're not the negative of each other. That wouldn't work. So we know that this bit is 0. So V squared plus U squared, I'll just move that over the other side. So that's another way of doing it. Part 2. Okay, so we can put U anywhere. We might as well put it on the x-axis, that'll be easiest. And then we want V to be there. And now what I would actually do is, because we know, you know, the special triangle, 1, 2, root 3, that would make U equals 2, because that's going to be the same as that, or it's twice the 1 there. And then V would be across 1 and up root 3. So that would be one possible answer. You could have also said something like U equals 1, and then V would be cis pi on 3, or that's cos pi on 3, plus I sine pi on 3, which would be 1/2 plus I root 3 on 2. There's actually like infinitely many answers to this question, so there's 2 possible ones. Question 16C, part I. This one's quite easy to do, just working backwards from the answer that we want. So we've got this n-1, and we've got a d of n-2. So that would be the number of derangements with n-2 people. So we've got to figure out how that works with this. Well, there are n-2 people left after Tom and the person that he swaps the hat with have been taken out. And the n-1 would be the number of people that Tom could potentially swap a hat with. So you've got n-1 choices for the other person to swap the hat with, and then once you've done that, you've got d of n-2. That's the number of ways that the rest of the people can swap hats with each other. So you would just say something like n-1 choices for who Tom swaps hats with, and then the number of choices for how to do the derangement for the remaining people is d of n-2, because there's n-2 people remaining. All right, part 2. Now this one was quite hard. A lot of people didn't even attempt this. So I'm going to go into a lot of detail about the whole problem-solving process with this question. So the first thing you want to do with a difficult question is just make sure that you read it really carefully and understand what's going on. So we're looking to find the number of derangements with n people. And if you expand this, you'll see it's n minus 1 times d of n minus 1 plus n minus 1 d of n minus 2. And this is what we found in part 1, where Tom just swaps hats with another person. So, and we're talking about the remaining possible derangements. So that's talking about the cases where Tom isn't just directly swapping a hat with someone. And so we want to show that that's equal to this. So that's what we have to prove. Now, what it looks like is that, so there's n minus 1 choices, and then there's d of n minus 1, which is the number of derangements with n minus 1 people. So why does that make sense that the remaining possible derangements would equal that? Well, what you might do to try to figure out why is maybe pick a small number, n equals 4, and try to list out all the derangements and see what happens. So I'm going to call the people A, B, C, and D, and like that one's Tom. So Tom could get B's hat, and then B can't have Tom's hat, so I can't write A there, because that would be part of the ones that we worked out in part 1, so this bit. We don't want to count those again, so I'm going to give B C's hat, and then I can't give C A's hat because then D would end up with D's hat, which we can't do because it's a derangement. So C has to have D's hat, and then D has to have Tom's hat. So that's one possible way we can do it. We could also give B D's hat, and then C ends up with Tom's hat, and D gets C's hat. And then that's the only way we can do it if Tom gets B's hat. Because I can't give B A's hat, because that's part of the third one. So there's only 2 ways to do that. And then, again, there's going to be 2 ways if Tom gets C's hat, and 2 ways if Tom gets D's hat. So you end up with 6 different ways of doing it. So we've got this n minus 1 there, and you can see that's the number of ways that Tom can pick a hat. He's got 3 choices of hats that he can pick. So that's the n minus 1. And then for each choice of hat that he has, there's 2 different ways that these people can arrange their hats. And that's because the person who, so you can imagine it as Tom swaps hats with someone. So in this case, it was he swaps hats with B. So you can imagine B is now wearing Tom's hat. And then B can't keep Tom's hat. He has to swap it with someone else. So B, C, and D, they have to do a derangement. So that's n minus 1 people, and they have to do a derangement. So you get D of n minus 1. So it's like n minus 1 choices for what hat Tom gets, and then with the n minus 1 remaining people, they have to do a derangement, because whoever Tom swapped hats with can't keep that hat, because that would give you one of those ones. So that's how that works. Now, the way that you phrase that, I'll just give you, these were the sample answers from the marking guide. So you can read through those if you want. And so those are the sort of ways that you can phrase it. It doesn't have to be like detailed mathematical, they're just writing it out in full sentences. Part 3. All we have to do with this one is replace the d of n with the formula that we worked out in part 2. So which was n minus 1 times d of n minus 1 plus d of n minus 2. And then just leave that as it is. Okay, and then I'm going to expand that. So n minus 1 times that, so you'll get n d of n minus 1 minus, so now the negative 1 times that. And when I do that times that, I'm not going to expand that bit because you'll see we've got an n minus 1 d of n minus 2 in the answer. So we probably want to just leave that as it is. And then that bit. And then this cancels with that. And we get that. So we want to make that into that. And you can see if you expand this, that just equals that. So we can just go straight to saying that. And that's it.